meeting. Anytime you want to consult, you can send me email or you can just send a post um, through Piazza. Okay, what I wanted to discuss today, well, I don't have prepared slides. I'm going to do a parang Blackboard style lecture. I wanted to discuss two things. Yung isa is yung coverage today. First is the frequency response. Of other amplifier technologies. Okay, then the other thing that I wanted to discuss is the method of open circuit time constant analysis. So these two things. At first, I was planning to just give examples, but when I was looking at the last lecture slides that were presented in UVLE, I thought that okay. I thought that may mga butas na baka kailangan or makatulong i-explain further, no? So first, let me discuss let's consider a common drain amplifier. Okay, let's consider a common drain amplifier. I'm going to draw a common drain amplifier, including the bias circuit. Okay, including the bias circuit, ano yung itsura ng common drain amplifier natin? No, we apply our input at the gate and we get our output at the source. No? So that will look something like this. No? For the meantime, I will call this VI prime. VI prime lang muna, no? And then the input resistance of my source, let me call Ri prime. And then this is normally coupled to your gate using a coupling capacitor, which is C1. Okay. And then I have my gate. My gate will have a source resistance, which in this case can represent also our load. So let me call this R sub L. No? So my output is at my source. So this is V sub O. And I will have a certain load capacitance C sub L. No? Okay. Your drain can be connected to VDD. Ngayon, ano yung kulang? Ang kulang dito is the circuit that will bias your gate. No? You need a biasing voltage here at the gate. Because if you don't have a biasing voltage here at the gate, this voltage may not put this transistor in the proper operating mode. That transistor has to be in saturation mode. So one of the most common methods of providing a bias, which we studied, is yung voltage divider natin. No? So this is R1 and R2. Okay. Now, what we do, we assume that C1 is large. No? Mean to say it is a short circuit at the input frequency. No? But we actually know that C1 will introduce a zero. This actually introduces a zero, so that at very low frequency, none of your input signal will actually reach the transistor. So actually, yung DC gain does not really exist. Kung meron kang C1, DC gain does not really exist. Because at very low frequency, this is an open circuit, so none of this signal can actually reach the gate. No? We took that up already last time. Okay, if I draw the small signal model, let's neglect. Okay, so I'll draw the small signal model. No? Okay, so I have V's of I prime, okay, R's of I prime. Okay, yung C1 ko, I can consider to be a short circuit. So what am I going to see? So this is to ground. I'm going to see R1 in parallel with R2, di ba? Dahil yung VDD is equivalent to a short to ground. So I'm going to see here R1 in parallel with R2. R1 in parallel with R2. Okay. And then I now am at the gate, no? So this is now my gate. Okay. From my gate to source, so let's say this is my source. This is my source. From my gate to source, I am going to have my gate to source capacitance, CGS. Okay, and then let's say this is my drain. Okay, from my drain to source, I have GM VGS, GM VGS. Okay. Between my gate and drain, I have my gate to drain capacitance. This is CGD. Okay, and then, so this is my source now. Notice at my source, I have RL and CL connected to ground, no? So I'm going to have here RL and then CL. So this is connected to ground, no? Okay, I'm going to discuss a side topic, no? And that side topic is body effect. No? So let me exit from this. Okay. So I showed you this slide when we took up the theory of operation of an NMOS. No? If you recall the theory of operation of an NMOS, usually your source is connected to your substrate, usually, no, but not all the time. And then you need a high enough value of VGS to create a channel underneath your gate, and that is what will allow current to flow from your drain to your source. No? This is your channel or your inversion layer. Ngayon, kapag common source, a common drain yung amplifier natin, our source is not connected to the substrate. No? If you recall, dun sa common drain amplifier, there's a resistor between my source and my substrate, no? And it is my substrate that is connected to ground, no? In other words, ito yung magiging itsura. Meron tayo ditong R's of S, no? And then it is your substrate or your bulk, sometimes we call this the bulk, that is connected to ground. Okay. What is the effect of the source not being connected to the substrate? Ano yung nagiging effect nun? Okay. there now is a voltage between your bulk and your substrate. Now that voltage affects the width of this depletion region. No? Because between your substrate and your channel, there is a depletion region. That's a PN junction. So magkakaroon yan ng depletion region. The more reverse bias between the base and the bulk and the substrate, the bigger your depletion region. What happens if your depletion region gets big? Itong channel lumiliit. The channel becomes smaller. In other words, the bulk to source voltage also affects the current that can flow from my drain to my source. If I had a voltage between my drain and my source. Okay, from a small signal perspective, okay, the change in the change in ID with respect to your bulk to source voltage, at VBS Q can be called your GMB, no? Your transconductance due to the bulk. No? And the change in ID, no? The change in your small signal drain current due to the GMB is just now equal to GMB times VBS, no? Where VBS is your change in bulk to source substrate. In other words, parang meron kang second, it's like you have a second controlled current source. And the variable that controls that current source is your bulk to source substrate. No? I don't have it here, unfortunately. No? The larger the bulk to source voltage, the larger the channel, the bulk is acting as a second gate. Okay, why did I introduce that? Because I saw it in the slides, no? Nandun sa slides, and you might be wondering ano itong second na transconductance na to, no? So I'll go back to the slides I was showing earlier. Okay, so we were drawing the small signal model. If you take a look at the UVLE slides, you're going to see here a second controlled current source. And this is GMB, okay, multiplied by VBS. Okay. So this is what we call the contribution of current due to body effect. No? So this is due to body effect. Okay. And that happens anytime there's a voltage between your bulk and your substrate. Okay, then we have RO. So kilala niyo itong RO. Okay. And our output is at the source, V sub O. Our drain, which is connected to VDD, is connected to ground. So ito yung magiging itsura ng small signal model. Okay, okay. Let's try to simplify things a bit. No? Okay, first, let me get this left side. No? Let's cut this out and replace it with its Thevenin equivalent. So I have VI and then RI and then R1 in parallel with I2. I can replace this with its Thevenin equivalent. Dapat marunong na kayo mag-Thevenin equivalent, no? And so I can just represent this by a signal voltage source in series with a signal a single resistance. No? And that's what I will now call VI and RI. No? So if you take a look at your slides, biglang lumabas ganito, no? VI, RI. And then sasabihin nyo dun sa slides, dun sa UVLE, ano nangyari sa mga biasing resistors? Well, the biasing resistors were already incorporated dito sa model na to. No? It's part of this Thevenin resistance. In fact, that will be this in parallel with this. No? It's part of the Thevenin resistance. Okay, what else? No? If you take a look at this component, CGD, that is actually from your gate. So this is now my gate. No? This is now my gate. Itong CGD is now from my gate to ground. So CGD is here, from my gate to ground. Okay. And then, if this is my source, between my gate and source, I have CGS. CGS. Okay. And my VGS is actually now here. No, this is VGS. Okay, so ito yung source ko. That is all the way to V out. No? Yung source is where I get my output. What else is connected to my source? No? From ground, so this is ground, notice, no? From ground to my source, I have a voltage source going upward. In fact, I have two control sources going upward. No? So let me draw the first one. So this is going upward. So this is GM VGS, no? Where ito yung VGS. So this is now connected to ground. Remember, ground is also bulk. No? Ground is also bulk. Okay. Now, where is this VBS? Itong VBS na to, no? Yung VBS is from my bulk to source, so this is actually VBS. I don't know if you remember, if you take a look at this voltage, so this controlled current source, okay, the quantity that controls this current is also the voltage across it. Pag tinignan mo to, no, ito lang, tignan natin to. Okay, I have a current going down here, whose value is GM VBS. Okay, but take a look at the voltage across that. Ano? The top, with respect to the bottom, is VBS. No, because ito, no, ito yung B, which is connected here, right? And then yung S is connected here. So meron din akong VBS rito. So what is this equivalent to? Do you remember? What is that equivalent to? If you think of this as a resistor, you just divide the voltage by the current. The voltage is VBS, the current is GM VBS. So if this is a resistor, what is this equivalent to? It's just a resistance 1 over GMB. B, no, I forgot the B. GMB. So this is just a resistance 1 over GMB. Okay. So meron ako ditong resistor na 1 over GMB. Okay. And then I have RO. And then I have RL. RL is also between source and ground. Then finally, I have CL. Actually, itong lahat nakakabit, no? Finally, I have CL. So this is what my small signal model will look like with all of my capacitors. Actually, there are two capacitors that I did not show here. Kasi ano yung capacitor sa MOS? Remember, we said that there are 4 capacitances sa MOS. There's CGS, that's from gate to source. CGD from gate to drain. And then there's from drain to bulk, and there's also from source to bulk. No? Kung naalala nyo, no? I drew that something like this, ano? This is your MOS. Diba? Meron kang CGD, CGS, tapos meron ka ritong CGD, tapos dito meron kang, no? Meron ka ritong CDB, no? And then dito meron ka ring CSB. No? So those are your different MOS capacitors, there are 4. No? So let's examine this, ano? Ano yung magiging effect ng ano yung kulang, no? Yung kulang is CDB. So you have a capacitance from drain to bulk. But your drain is connected to bulk. No? Kasi yung drain mo is effectively short-circuited to ground. So your drain is actually connected to bulk. So CDB is actually shorted out. So walang effect yung CDB. Okay, so what's the other one? CSB. So CSB is from source to bulk. No? From source to bulk. Okay, but if you take a look, from source to bulk is actually across the output. No? Source to bulk is actually across the output. So yung source to bulk capacitance natin, you can actually add to Cs of L. Cs of L. Now normally it will be small, it will be negligible with respect to Cs of L, no? But you can actually add that to Cs of L. Okay? So we can call this Cs of L prime, which is equal to Cs of L plus CSB. Okay, and then I mentioned that CDB, this is shorted because your drain to bulk is shorted. And then you can combine these three resistors. Can combine. So let's call that combination, for lack of anything else, let me just call that RX. Better RL prime, so that we're consistent with the notation. RL prime. So finally, I have a simplified V sub I, R sub I, CGS, so teka, ayan. This is CGD, this CGS, no? CGD. CGD, and then this is CGS. So this is my gate, this is my source, this is VGS. And then dito, I only have 3 remaining components. So this is now pointing up, GM, VGS. And then RL prime, and then CL prime. Then this is now V sub O. So you can take it away from here. I mean, to do frequency analysis, you just convert your capacitances to impedances. No? I mean, ginawa na natin yan many times. I had examples of that. So from here, you can compute for AV, which is a function of S. You can compute for GM, which is a function of S, RI, and RO. And all of this will have a frequency response. And how do you get the frequency response of all of this? You replace S with j omega. Okay. Any question? Any question? So the key is just to be able to derive the small signal model, which includes all of the capacitances. Oh, okay. By the way, no, if you get, I just repeat myself, no, if you get the frequency response of this, there's going to be a parang DC gain, di ba? And then at some point, it's going to fall off. Okay. Magkakaroon to ng, if you get the frequency response of the, let's say, the frequency response of the gain, no? So this is a AV, no? The magnitude of gain. Okay. Usually you have a DC gain, no? And then at a certain frequency, so we call this frequency, sometimes we refer to this as omega h, no? Because that is the 3 dB point, no? So this is where it starts to roll down. No? That's where it starts to roll down. And we know that the actual curve will be about 3 dB from the DC gain. No? Okay, and then depending on how many poles there are, diba? Depending on how many poles, okay, it might roll down several times, no? 1, for example, 2, and so forth, ano, diba? And then when you get to the 0, because the 0 is in the denominator, it might recover, no? Something like that, no? Kasi yung 0 adds, no? Adds 20 dB per decade, yung pole subtracts 20 dB per decade, no? So it goes down, no? But usually this is our point of interest. No? This is what we call the bandwidth because we design the circuit to be operating here. No? Between this and this, no? Because after omegas of h at this frequency, bumabagsak na, no? And you know that when you hit omegas of t, ano yung omegas of t? What do you call that? The transition frequency. No? That is the frequency at which yung input and output are equal in amplitude. And beyond omegas of t, no? So this is omegas of t, bumabagsak na. That's when your output is now smaller than your input. Okay, but and I'm just reminding you, no? But like I said, because of this capacitance, your gain at DC is not really 0. No? Yung magiging itsura niyan talaga is something like this. No? I'm just repeating myself, no? It's something like that. Because at very, very low frequency, yun nga, no? There is none of the input signal that reaches the output. Okay. So you have here also a certain omegas of L. We call that omegas of L. It's the low frequency value where your gain is 3 dB below the what we earlier called the DC gain, no? But actually this term, this gain is more aptly called your mid-band gain. No? This is your mid-band gain. Okay. So I just want to give you some insights. Okay, so this is caused by this gain being equal to 0 here is caused by your coupling capacitors or your bypass capacitors. Okay, any questions? Okay, what if this had been a common emitter amplifier? Kasi ang ginamit kong example is sorry, not common emitter, a common collector amplifier. Ang ginamit kong example was common source, no? Ang katumbas ng common source sa BJT is your common collector. What is the difference between the model of the common collector and the BJT and the MOS? It's just R pi. Yun lang yung kaibahan, no? Sa MOS, yung R pi natin is equal to infinity. Okay? Sa BJT, meron tayong R pi. Where does R pi exist? R pi exists between your base and your emitter. No? So if we take a look at the small signal model, the only difference here, your base, ang katumbas nun sa MOS is your gate, your emitter, your drain. So if you take a look at the BJT, meron ka lang na R pi that will be in parallel with CGD. There will be a resistor in parallel with this. And then you just have to take that into consideration in your computations. So actually, it's easier to compute pag MOS dahil wala ka nung R pi na yun, no? Pag BJT, meron kang R pi dito. Any questions? Sige, tuloy natin, no? One other configuration that I wanted to discuss, common gate. Again, no, we'll start with the common gate. But if you consider ano yung katumbas ng common gate, common base, if you consider the common base, the only difference will be yung R pi. That's the only thing that you have to incorporate. So let's take a look at common gate. Again, ang starting point ko is with biasing. So with biasing, what will this look like? Okay. Where do I apply my input sa common gate? I apply it in my source, and then I get my output in my drain. So, okay, let me call this RL. Let me call this RS. I apply my input at my source. So how do I apply my input? Okay, here I have C. Let's call this C1. And then I have my source signal, VI. Again, let me just call this for the meantime VI prime and RI prime. And I get my output at my drain. No? So let's assume that my load is capacitive. Let me call this CL, and this is V sub O. No? Ngayon, pag minsan, meron tayong coupling capacitor din dito, no? To get rid of the DC component of my output. No? There might be a coupling capacitor here. But again, we assume that these coupling capacitors, no, especially when we're doing high frequency analysis, you can assume them to be short circuits. Okay, so what is not shown is the biasing. So ano yung alam nating biasing? The most common type of biasing is yung resistor divider para sa MOS. So R1 and R2. Okay, meron pang kulang to, no? Because with respect to my input signal, this should be connected to ground. No? Kaya nga tinawag na common gate. Now, how do you connect that to ground? Through a capacitor. So again, with respect to DC, the capacitor is open. That establishes your bias. But with respect to AC, this capacitor is short. It's called the C2, and that connects my gate to ground. So we assume that C1 and C2 are large. They will affect the low frequency characteristics, no, but they have minimal effect on the high frequency characteristics. Yun typical, no? Pag yung coupling capacitors or bypass capacitor, they affect the low frequency but minimal effect on the high frequency. That's why we just consider them to be, or we disregard them in our high frequency analysis. Let me draw the small signal model. I'll draw the small signal model. I'll retain first the transistor. Okay. So I have VI prime. I'll start the input. I have VI prime, RI prime. Okay, so my capacitor now is a short circuit. Now I'm at my source. And what do I have? I have a resistor to ground. No? By the way, so again, this is a case where your source is not connected to your bulk. So there's going to be a source to bulk voltage. But then for this particular case, we can disregard that. Let's just disregard in effect, let's disregard the body effect, to simplify the analysis. So that's another assumption. Let's neglect the body effect. Okay, so ito yung source ko. Okay, so ganyan yan. Okay, so this is now my drain. What I have connected to my drain? I have connected to my drain my load resistor, RL, and my CL. So ito ngayon yung output ko. Okay, from the point of view of small signal, from the point of view of AC, this is connected to ground. What happens to R1 and R2? Yung R1, this is from gate to VDD, but VDD is ground, so ito yung R1. Yung R2 is from gate to ground, so ayan. In effect, shorted out yung R1 at saka R2. No? If you take a look at this is R1, this is R2. R1 and R2 are just shorted out. So in effect, R1 and R2 will not affect the small signal analysis of this particular circuit. Okay. So I can now disregard, in effect, I can disregard R1 and R2. Nakikita nyo yan, di ba? Ito just shorted to ground R1 at saka R2. Okay, so anong next na gagawin ko? Now I'll replace this. Let me replace this with its small signal model, including all of the capacitances. But first, I'm going to do the same thing. I can get the Thevenin equivalent of this. Pwede kong kunin yung Thevenin ito. And when I get Thevenin, I will just come up with, imbis na VI prime, VI na lang, let me call it VI, and RI. Where RI is just RI prime in parallel with RS. Pag tinignan mo, RI is equal to RI prime in parallel with RS. Simple Thevenin equivalent of a resistor divider. Okay, so let me now convert this to its small signal model, including all of the capacitances, the parasitic capacitances. So I have VI, RI, which brings me now to my source. So I'm now at my source. Okay, from my source to bulk or source to gate, no, so remember my ground is also my gate. No? This is my gate and at the same time and my bulk. No? So from source to gate, I have a capacitor. Okay, this is CSG. CGS rather, no? Usually we say CGS, not CSG. Okay, but I also have a capacitance from my source to bulk. No? I call this CSB. Right? Ito, no? I have source to bulk, no? And gate to source. Okay? Kasi nagkataon, itong point na to is shorted to this because my gate is shorted to ground, no? And so these two end up being in parallel, your gate to source and your source to bulk. Okay? So remember this is ground, no? Here I have my drain. No? This is my drain. Okay, between my source and drain, what do I have? I have my controlled source here. No? This is GM VGS. Now, where is VGS? VGS is from my gate to source, so yung VGS will be here, no? Plus minus VGS. Where yung plus ko nasa baba because my gate is down and my source is up. So take note that the polarity of VGS is plus sa baba, negative sa taas. Now, what else do I have between my drain and source? I have Rs of O. Meron akong Rs of O dito. Rs of O is parallel to my controlled current source. And then between my drain and gate, what do I have? I have a gate to drain. I have CGD. No? My gate to drain capacitance. Again, that's this. Itong capacitor na to, gate to drain. And then my gate to bulk, my drain to bulk, no, is also in parallel. No? So this is my drain to bulk. What else do I have? And then I have these two in also from my drain to my bulk, no? Or drain to ground. So I have RL, and then I have CL, and then this is now my V sub O. Okay. So I can combine these two. Let me call this C sub S. This is CGS plus CSB. I can combine this with this. No? Let me call that CL prime. That's CL plus CGD plus CDB. So finally, what am I left with? I have VI, RI, CS, GM, VGS, where this is VGS minus plus VGS, RO, okay, RL, yeah, it's not RL prime, no? It's RL, and then I have CL prime. This of O. So again, this is the model that you're going to derive all of your hybrid pi parameters. No? So you can, again, you can compute for AV, which is a function of S, GM, which is a function of S, RI, which is a function of SRO, which is a function of S. And you can compute for all of that, no? Using the techniques that we already learned. Typically naman, it always requires, no? Typically, it always requires two KCL equations. Usually, you'll have a KCL equation at the output and a KCL equation at the input. Then you have to just learn how to manipulate your KCL equations so that you can get the correct ratio. No? For AV, it's the ratio of V sub O over VI. No? For GM, it's the ratio of I sub O over V sub I. No? Where I sub O is determined with your output shorted. No? You have to short your output to be able to get I sub O, and then you get the ratio of I sub O over V sub I. That's for GM. Then RI is VI over II, and RO is VO over I sub O. Okay. No? To get RI, you just need to apply a test voltage at the input, which is in effect this one. Right? And to get RO, you need to apply a test voltage at the output. So you already should be used to all of those by now. Okay. What if this was a BJT? Saan papasok yung RPi? What if this were a BJT? Where would your RPi be? Anyone? Okay. Yes. In parallel with? Yeah, that's right, no? In parallel with CS. No? Kasi yung gate natin is effectively or equivalent to the base. Your source is equivalent to your emitter. So your RPi will be here, no? So how do you again simplify the analysis? Well, if you had RPi, well, dito, no? We could have done it here, no? Well, di pala, no? We haven't converted yet this one. But if you had RPi here, no, or RPi here, you could have done another Thevenin, no? Para yung magiging VI mo, siguro pwede na natin gawing VI double prime, no? In other words, if you had RPi between this point and this point, you can do again a Thevenin para ma-simplify lang yung input natin. Okay. By the way, no, warning, no, when you get V sub O, okay, you have V sub O over this V sub I, no, but this, remember that this V sub I is not your original V sub I. No? Yung original V sub I natin is V sub I prime. So just a warning, if you get AV, that should be V sub O over your original V sub I. So babalikan nyo yung relationship, babalikan mo rin yung relationship between V sub I and V sub I prime, which is your original V sub I. So I just wanted to point that out, no? Because we did this Thevenin thing just to simplify things. But remember that AV is V sub O over your original V sub I. Okay? Okay, one last topic, which I saw included in the lecture slides. No. Okay, what does this last topic address? No? It addresses this question. No? Is there a convenient way of approximating omegas of H? Yung omegas of H, this is the frequency at which your mid-band gain will drop down by 3 dB, no? Because omegas of h actually dictates, that dictates your bandwidth. Your bandwidth is effectively the range of frequencies which your amplifier can operate. No? Is there a convenient way of approximating omegas of h? Kasi if you take a look, lahat ng mathematics nito is so involving, no? Ang daling magkamali, di ba? When you put the actual figures in, isang maling pindot lang sa calculator, patay ka na, no? Luckily, you have your simulators, no? So I would imagine in the future, if you get into this career, you would probably use your simulators more than doing hand calculations, no? But it's important that at least you know the basis for all of this. That's very important, because if you just use your simulators blindly, wala kang insights, no? But when you know these things, you can develop certain insights, no? Anyway, that's just an aside. Is there a convenient way of approximating omegas of h? There's what we call the method of open circuit time constant analysis, no? Okay, this is what your textbook calls it, no? This is Sedra and Smith, no, calls it the method of open circuit time constant analysis. It's also called the zero value time. It's also called zero value time constant analysis. Okay, and what are your steps, no? So first, you set v of I to 0, in which case you replace with a short circuit, no? Replace with a short circuit. Okay. Second, you consider each capacitor separately. No? You set all caps to 0. No? Kaya tinatawag na zero value, no? Set all caps to 0. Okay. Actually, if you set a cap to 0, it becomes an open circuit. Because remember, impedance is proportional to 1 over C. If C is 0, your impedance is infinity. It becomes an open circuit, no? So set all caps to 0, so this is like an open circuit. Okay. Except for the capacitor of interest. For which we determine the equivalent resistance looking into that capacitor's terminals. Anyway, I'll provide an example later, no? So let's say meron tayong tatlong capacitor. We consider each capacitor separately. Okay. So if we're considering capacitor 1, we make capacitor 2 and capacitor 3 open circuit, no? And then we get the equivalent resistance of the circuit looking into capacitor 1's terminals. Okay. And W's of H will approximately be equal to 1 over the summation of all of these capacitors, Ci times R I, no? The equivalent resistance. So Ci is your capacitor, and then Ri is the equivalent resistance looking into Ci. that will be your approximate value of omega sub h. No? So let's take an example. Say your common source amplifier. Take a common source amplifier. So a starting point would be the small signal model with the capacitors. So my small signal model, I have my VI, R sub I, and then, so this is now my, itong point na to is my gate. No? So I have CGS. No? Bottom is my source. So this is VGS. And then this is my drain. So here I have CGD. Okay. From drain to source, my GM VGS. Okay. And then, yeah, let me just use RL, no? But we'll just assume that RL already takes into consideration mga things in parallel with it, no? For example, yung mga RO, whatever, nandun na yun, combined na into, lumped into RL, no? Just like RI might already take into consideration things that we did to simplify this. No? Para lang hindi nakakalito masyado. No? Okay, and then of course you have your CL. Then this is V sub O. So we take it one capacitor at a time. So for example, for capacitor CGS, okay, if this is an open circuit, kasi we make this an open circuit, If this is an open circuit, hindi na makikita nitong capacitor yung circuit sa kanan. The circuit on the right will now be isolated from CGS. No? And then we make V sub I equal to a short circuit. No? We make V sub I equal to 0. So what will be left? All that will be left is R sub I. Okay. And then this is my CGS. No? What will be the equivalent resistance looking into the CGS terminals? No? This is just equivalent to RI. No? Let me call it something different. Let me call this RGS. No? RGS, the equivalent resistance looking into the terminals of CGS, that will be equal to R sub I. Okay, let's consider C sub L, no? Or C sub L. Okay, if I'm considering C sub L, I make this an open circuit. I also make this an open circuit. Okay. So, but I will still draw this. No? That this is a short circuit. I-drawing ko na rin, ano? Because okay, this is going to be VGS. That's an open circuit. No, wala yung capacitor, wala yung CGD. I will have here GM VGS. I'll have here RL. And then this is my C sub L. No? So I have to get the equivalent resistance looking into C sub L's terminals. No? So let me call this R sub L. Well, Sorry. It's okay, no? You're going to see it doesn't conflict anyway, no? Okay, ano yung VGS? Zero, di ba? Dahil wala kang current dito, so your voltage will be zero. So that makes this zero. So in effect, ito nagiging open circuit lang. And you see that the equivalent resistance looking into CL terminal is really just Rs of L. Right? Rs of L lang talaga ang nakikita ng terminals ng Cs of L. Now, yung magiging komplikado ng katiting is yung CGD. So let's consider CGD. Okay, I short this, I keep this open, I keep this open. So this is my CGD. Okay, I have Rs of I here. This is shorted. This is GM VGS, where this is now VGS. And then I have Rs of L. Cs of L is open. Cs of L is open. No? I want to get the resistance looking into CGD's terminal. No? The terminals of CGD. No? In other words, RGD. How do I do that? How do I get the resistance looking into the terminals of CGD? Well, first of all, you take CGD out. Dapat tanggalin mo yung CGD. Because you're just looking into its terminals. So, sige, let me draw it again. So this is Ri. Okay, so this is G. This is D. How do I get the resistance looking into these two terminals? What did you learn if you're getting the equivalent resistance and you have a controlled or a dependent, a controlled source? What do you have to do? Yeah, you have to apply a test voltage or a test current. So in this particular case, let me apply a test current. But it doesn't matter. It can be a test voltage, it can be a test current. So let me apply a current. And what I have to do to determine the VDG and my resistance, no, RDG will be equal to VDG divided by Is of T. That's the way. You learn that in 1, 2, 3, no, when you're getting the equivalent resistance looking into a set of terminals. Okay. V's of G is equal to VGS because this is ground. No? Okay. Therefore, well, anyway, sige, let's apply KCL at D. KCL at D. So KCL tayo rito. You have Is of T is equal to V's of GM, VGS, but VGS is V's of G. No? Okay. Plus V's of G, V's of D rather, over RL. No? You have this current going down here, and then this current going down here. Yeah. Okay, but what is V's of G? No? Hindi ko pala tinuloy ito. V's of G is VGS, but you have a current IT flowing up here, right? So V sub G is actually minus Ri times IT. Kasi meron akong IT dito, no? IT, right? Because of this current source, you're going to have IT flowing up here. So V sub G is actually minus Ri times IT. So I have minus GM Ri IT plus V sub D over RL. Okay. Okay. Let me compute for V sub D. No? V sub D is now equal to RL, and then I have IT RLIT. Okay, itong term na to, lilipat sa kabila. So I'm going to have 1 plus GM RI. Tama? One plus GM RI times RL. Yeah, tama, no? Correct me if you see something wrong. Okay, sometimes nalilito din ako. So what is now VDG? No? VDG is equal to VD minus VG, which is equal to RL IT 1 plus GM RI minus RI IT. No? Minus or plus, magiging plus RI IT. So finally, RDQ is VDG over RDQ is VDG over IT. So nagka-cancel out lang yung IT. So this just becomes RL 1 plus GM RI plus RI. This is what we were looking for. Just want to make sure I have the right results because I did this prior to this. Yeah, tama. Okay, so finally, what is WH? No, that's going to be equal to 1 all over RICGS plus ito, no? RLCL plus RL 1 plus GMRI plus RI multiplied by CGD. So this is one way of trying to predict what your 3 dB fall off frequency is going to, 3 dB frequency is going to be at high frequency, no? Kung saan magpo-fall off to 3 dB. And that's it. That's the last thing that was introduced in the lecture notes. Any questions? And so again, no, we're not going to see each other anymore after today, but it's still some ways before the end of the semester. We have the Christmas break in the middle. You still have your homeworks and your quizzes to complete, no, and then you have your second exam, the final exam. I think sometime the second week of January. So I hope you don't waste too much of the Christmas season. At the same time, still enjoy the Christmas season. Okay. Merry Christmas na lang sa inyo. Yes. No? Na-release na ba? I wasn't able to check whether it was released. Why don't you ano, no? Make a formal request. Yeah, maybe through Piazza kasi kung marami kayo that are in the same situation, pwedeng pag-usapan, no? Pwede naman pag-usapan ng mga handlers. Okay. Any other questions? So good luck. Good luck to you not only in this course but the rest of your courses. Okay. Thank you.